Thank you everybody for being here today. Today I'm going to talk about my Chi 21 paper, SuperResolution Capacitive Touchscreens. And this work was conducted during my time at Carnegie Mellon University with my collaborators Xiangyu and Chris. For a long time, researchers already set out to understand how we can extend the capabilities of touchscreens. Here in the end 2000s, researchers tried to extend tabletops by integrating tangible user interfaces. And back then they used infrared technology to track the tangible object, the same technology that's been used at the time to track also the finger. However, in contrast to these infrared sensors, today's technology, which are capacitive touchscreens, the resolution is way lower. So for instance, one example here is this April tag with a size of 24 by 24 millimeters. And you can understand this as the bottom side of a tangible user interface, which is placed on top of the touchscreen. And as a result, we see here 4 different orientations and variations of the capacitive image that is produced by the tangible itself. And here it is pretty clear that information got lost between the tangible that is placed on the screen and the then recorded data information from the tangible. And here we really set out to understand and explore approaches to upscale the information and really retrieve the information that is hidden in the capacitive images. And one approach here that we pursued in this paper is using geometric superresolution, an approach that is already long applied in fields like astronomy and biology. And the idea here is taking multiple raw images and then stack them, combine them and upscale them in order to retrieve information from all of the images combined, to then have a super resolved image, which you can see here for the planet on the right side, while seeing multiple raw images on the left side. So a similar approach we used now for the capacitive data. And for the pipeline, we have the physical marker that is placed on the touchscreen. And by motion induced by a human, we get multiple differently looking capacitive images. Those images can then be upscaled, aligned and stacked on a high level speaking, and then they give you a super resolved capacitive image. And if you look at the image, you can see the information clearly in the super resolved image, however not in the capacitive raw image. So to evaluate our approach, we set out a number of experiments. And one of the experiments I want to present you today is here using multiple April tags that we designed and printed, built as physical tangibles in different sizes, 4, 6, and 8 millimeters as one of the pixels size. And we can really see how our approach outperforms in accuracy, so in recognition, over the baseline for the very small sizes of tangibles. For traditional objects, however, this brings augmentation with it. So in a follow-up, we looked at the geometric shape of an object itself, such as in this example, the coin size, to recognize coins. And this already brings me to my conclusion. I presented to you today how geometric superresolution works in principle and how we applied this method to capacitive sensor data and therefore enable tangible recognition on today's capacitive devices. I gave you a bit of the insight that we gained from our evaluation, in which I showed you how we really can especially improve when there are small details in tangible objects. And I also gave you an introduction into 2 potential use cases which we see that where really super resolution can shine to enable new applications in the future. Thank you very much for your attention.